Every teacher you ever had taught you the same rule about heat, and you learned it with your own body long before anyone ever put it into words. Stand close to a fire and you are warm. Step away from it and it cools. The farther you go from the flame, the colder it gets. It is the most dependable rule you know, so obvious it hardly seems worth saying. And the sun breaks it. The surface of the sun burns at about 10,000 degrees, but its outer atmosphere, the part farther from the fire, is not cooler. It is hotter. Up to 300 times hotter, 1 to 3 million degrees, climbing as you move away from the source, as if you stepped back from a campfire and burst into flame. For more than 80 years, no one could explain why. And then, on Christmas Eve, in the year 2024, we did something to find out that should never have been possible. We flew a machine straight into the sun. Get comfortable. Hit subscribe if you're new here, because by the end of this, the most familiar light in your sky is going to feel stranger than you ever thought possible. Now, let us slowly ease into this. Part 1. The Silence on Christmas Eve. On the 24th of December in the year 2024, while most of the world was wrapping presents and half watching the same holiday movies it watches every year, a small team of people sat in a quiet room in Maryland and waited to find out whether the machine they had spent more than a decade of their lives building was still alive. They were not celebrating. They were watching numbers on a screen, and the numbers were describing something that, not so long ago, serious scientists had called physically impossible. A spacecraft roughly the size of a small car was falling directly into the atmosphere of the sun. Not near the sun, not close to the sun in the way that we usually mean when we talk about getting close to something enormous and dangerous. Into it. Into the outermost layers of an actual star. The one our entire world has orbited for 4.5 billion years. The one every ancestor you have ever had looked up at without the faintest hope of ever reaching it. And it was moving fast. At the moment of its closest approach, this spacecraft was travelling at about 430,000 miles per hour. To put a number like that into something your body can feel, imagine leaving New York and arriving in Los Angeles roughly 20 seconds later. That is not a figure of speech. At that speed, the width of an entire continent passes beneath you in about the time it takes to read this sentence. It was the fastest object human beings have ever built. Not the fastest aircraft, not the fastest rocket, the fastest thing of any kind that our species has ever made move. I want you to sit with the strangeness of that, because the people in that room were sitting with it too. They had a name for this moment. They had rehearsed it, modelled it, argued about it for years, and now it was simply happening out there, tens of millions of miles away, entirely beyond their reach. Because here is the part that made that Christmas Eve so difficult for the men and women watching those screens. As the spacecraft dropped toward the sun, it went silent. It was supposed to. They knew it would. When you fly that deep into the sun's atmosphere, the sheer intensity of the radiation pouring off the corona completely overwhelms any radio signal a small spacecraft could ever hope to send back home. There is no way through. So the plan, from the beginning, was that the probe would disappear into a communications blackout, a stretch of time in which it would be utterly alone, flying on nothing but its own preloaded instructions, unable to hear a single new command from Earth, and unable to send back a single word about how it was doing. There is a difference, though, between knowing something with your mind and living through it with your whole body. You can plan for silence for 10 years. You can write the silence into the mission timeline, put it on the schedule, brief every engineer on exactly when it will begin and exactly when it should end. And still, when the moment comes and the last thread of contact thins out and vanishes, and the screens simply stop telling you anything at all, it lands in a way no plan quite prepares you for. Somewhere out there, a machine you have nursed through 6 years of careful, patient manoeuvring has just flown into a star, and you have no way of knowing whether it survived the first second of it. So they waited. That was the whole job now. Not commanding, not correcting, not adjusting. Just waiting through the hours, through the blackout, while the spacecraft did the one thing they had built it to do, and they could do nothing at all to help it. Think about where it was during that silence. 3.8 million miles from the surface of the sun. That number sounds large, and in ordinary human terms it is almost meaningless, but let me give you something to measure it against. Mercury, the innermost planet, the little scorched world that huddles closer to the sun than anything else in our solar system, never comes within about 28 million miles of the solar surface. This spacecraft was more than 7 times closer to the Sun than Mercury ever gets. It had gone to a place no planet has ever been, a place we had only ever studied from a comfortable, cowardly distance, squinting at the Sun through telescopes and filters from tens of millions of miles away. And now, for the first time in the entire history of life on Earth, something we made was inside it. This is the story of that machine. It is the story of how it was built, and why almost everyone thought it could not be done, and the strange, quiet, stubborn man it was named after. A man who was told he was wrong and turned out to be right about the very thing this spacecraft was flying into. It is the story of a mystery about the Sun that went unsolved for more than 80 years, a mystery that seems, at first, to break one of the most basic rules of how heat works, a rule you have known since you were a child standing near a fire, and it is the story of what we found when we finally stopped looking at our star from a distance and reached out and touched it. But before any of that, I want to leave you here for a moment, in that room, in that silence, on that Christmas Eve, because everything that follows, all the physics and all the engineering and all the history, was, in the end, in service of this one nervous, human, breath-holding wait. A team of people who had given years of their lives to a single machine, sitting in the dark, listening for a sound from a star, not knowing if it would ever come. Now, let's go back and understand what they had actually done, and why it should never have been possible in the first place. Part 2. What it really means to touch the Sun. When you picture the Sun, you almost certainly picture a surface, a bright, blinding disk, a ball of fire hanging in the sky, a definite edge where the Sun stops and space begins. It is a natural way to see it. It is also, in a quiet but important way, wrong, and understanding why it is wrong is the first step toward understanding what this spacecraft actually did. The Sun does not have a surface the way the Earth has a surface. There is no solid ground out there, no crust, no shoreline where you could stand. What looks to us like the Sun's surface is simply the layer where the Sun becomes transparent, the depth at which its churning gas stops being thick enough to trap light and lets that light finally escape toward us. We call that layer the photosphere, which just means the sphere of light. It is the part that glows, the part you would draw if someone asked you to draw the Sun. And it burns at around 10,000 degrees Fahrenheit, which is already a temperature so far beyond anything in your daily experience that your mind cannot really hold it. It is hotter than anything you have ever touched, hotter than lava, hotter than the inside of a furnace, hot enough to reduce any material you have ever held in your hand to vapor in an instant. But here is the thing, almost nobody is told. That blinding surface is not the outermost part of the Sun, and it is not the most dangerous part either. Beyond the photosphere, above it, stretching outward for millions upon millions of miles in every direction, there is more Sun. There is an enormous, faint, almost invisible outer atmosphere, a vast envelope of superheated gas so thin and so dim that from Earth we can normally only see it during a total solar eclipse, when the moon slides in front of the bright disk and blocks the glare. In those few minutes of eclipse darkness, a pale, ghostly crown of light appears around the black circle of the moon, reaching out into space like the petals of some impossible flower. That crown is the Sun's atmosphere, and its name, fittingly, is the corona, from the Latin word for crown. The corona is the real destination. When we say this spacecraft touched the Sun, we do not mean it plunged into the fusion furnace at the centre, or even that it skimmed the blazing photosphere. We mean that it flew into the corona, this immense outer atmosphere, and travelled through plasma that genuinely belongs to the Sun itself, gas that is part of the star, held in the Sun's own grip, governed by the Sun's own magnetic field. That is what makes it a touch. For all of human history, the corona had been something we could only watch from far away, a faint smear of light in an eclipse photograph. This machine went and flew through it. And it was not even the first time. There is a moment a few years earlier that scientists marked as the true first touch, and it is worth pausing on, because it tells you how carefully they defined this achievement. The Sun's atmosphere does not simply fade smoothly into empty space. There is a particular boundary out there, an invisible line called the Alfvén surface, named after a Swedish physicist. Below that line, the Sun's magnetic field is strong enough to keep a firm hold on the plasma, and the gas still moves in a kind of conversation with the Sun, connected to it, able to send waves and ripples back down to the star. Above that line, the plasma finally breaks free, streaming outward into the solar system, no longer able to talk back to the star it came from. Crossing below the Alphen surface is, in a real physical sense, the moment you enter the sun's atmosphere rather than merely brushing its exhaust. On the 28th of April in the year 2021, this same spacecraft dipped below that line for the first time. It spent about 5 hours down there, some 8 million miles above the photosphere, inside the magnetically dominated corona, in genuine contact with the sun. That was the first time in history any object built by human hands had entered the atmosphere of a star. And the passage we have been talking about, the one on that Christmas Eve in 2024, went far, far deeper and far, far faster. So when I ask you to let go of the idea of the sun as a simple ball with a clean edge, this is why. The sun you picture is only the innermost, brightest part of something much larger and much stranger. The real sun reaches out for millions of miles, an ocean of thin, superheated, magnetized gas, mostly invisible, endlessly in motion. And it is in that ocean, in the corona, that the deepest mystery of our star has been hiding. Because the corona does something that, on the face of it, should not be allowed to happen. It breaks a rule about heat that you have understood, without ever having to be taught it, since the first time as a small child you reached towards something warm, and then, feeling it, pulled your hand back. It helps, I think, to try to picture the true size of the thing we're talking about. When you look at the sun in the sky, you're seeing that bright disk, the photosphere, and it seems to have a clean, hard edge, a definite boundary where the light stops. But the corona has no such edge. It does not end at some tidy line and give way to empty space. It simply thins and thins, growing fainter and more tenuous, reaching outward for millions upon millions of miles, so far that in a very real sense the sun's atmosphere extends past the orbits of the planets. The solar wind that Eugene Parker predicted, the wind that washes over the Earth, is in a way the outermost reach of that atmosphere, still blowing past us at 93 million miles, still carrying the influence of the star. When you stand in sunlight, you're not merely being warmed by a distant object. You're standing inside the faint, far outer edge of the sun itself. That is a strange thought to hold, and I want to let you sit inside it for a moment. The sun is not a ball you look at from the outside. It is a place, an environment, an ocean of thin, superheated gas and magnetic field, and the Earth is not next to that ocean, but immersed in it, floating in the sun's outermost currents, sheltered only by the invisible magnetic bubble our planet generates around itself. Every day of your life has been lived inside the atmosphere of a star. You simply never had a reason to think of it that way, because the part of that atmosphere you live in is so thin, so faint, so gentle by the time it reaches us, that it feels like nothing at all. And yet, trace it back, follow it inward toward its source, and it grows thicker and hotter and more violent until you arrive at the corona, the dense, blazing, million-degree heart of that atmosphere, the place this spacecraft was built to enter. For most of human history, the only time anyone ever saw the corona was during a total eclipse, in those few minutes when the moon slides perfectly in front of the sun and blocks the overwhelming glare of the photosphere. In that sudden false twilight, with the bright disk hidden, the corona leaps into view, a pale halo of light streaming outward from the black circle of the moon, wispy and structured and reaching out in delicate rays and loops. People travelled across the world to stand in the path of an eclipse and glimpse it. Whole scientific expeditions were mounted just to photograph those few minutes. The corona was, for almost all of the human story, something you could only ever steal a brief look at, once in a long while, under the rarest of circumstances. And now a machine had flown straight into it and stayed. Now, let us look at exactly what that rule is, and exactly how the sun breaks it. Part 3. The rule the sun refuses to obey. There is a rule about heat that you learned without anyone ever sitting you down to teach it. You learned it with your body probably before you could speak. If you stand near a fire, you are warm. If you step back from the fire, you are cooler. Take another step back, cooler still. Keep walking away, and eventually you feel nothing at all, just the ordinary temperature of the air. The closer you are to the source of the heat, the hotter you are. The farther you go, the colder it gets. This is so obvious that it feels almost insulting to say out loud. It is the way the entire world works. It is the way a campfire works, and a stove, and a radiator, and the engine of a car, and every hot thing you have ever stood beside. And it is not just common sense. It is physics, one of the most dependable rules we have. Heat flows from hot things to cold things, spreading outward, thinning as it goes, always moving from where there is more of it to where there is less. Energy radiates away from its source and weakens with distance. This is as close to an unbreakable law as anything in nature. Everything you have ever experienced obeys it. The sun does not. The surface of the sun, the photosphere, that blinding layer we talked about, sits at around 10,000 degrees Fahrenheit. That is the source. That is the fire. Now, following the rule you have known your whole life, you would expect that as you move away from that surface, up and out into the corona, into the thin outer atmosphere millions of miles from the center of all that energy, the temperature should fall. It should cool down. It should eventually approach the deep, brutal cold of space, which sits at hundreds of degrees below zero. That is what should happen. That is what happens with every fire you have ever stood near. Instead, the temperature does the opposite. As you rise off the 10,000 degree surface and move outward into the corona, the temperature does not drop. It climbs, and it does not climb a little. It skyrockets. The corona, that faint ghostly crown, the part of the sun farthest from the surface, reaches temperatures between 1 million and 3 million degrees Fahrenheit. Let me say that again, slowly, because it is genuinely one of the strangest facts in all of science. The thin outer atmosphere of the sun, the part that is farther from the furnace, is up to 300 times hotter than the surface directly beneath it. Sit with that for a moment. Walk away from a campfire and it gets 300 times hotter. That is what the sun does. It is as if you stepped back from a fireplace and burst into flame. It is as if the air at the far end of your kitchen were hotter than the burner on your stove. It is a violation of the most basic intuition you have about how the world behaves, and it is not a small effect at the edge of measurement, not a rounding error, not a subtle anomaly that only a specialist could care about. It is enormous, obvious, and staring us in the face every single day in the light of the star we have watched since before we were human. Physicists gave this puzzle a name. They called it the coronal heating problem, and for more than 80 years it stood as one of the greatest unsolved mysteries in all of astrophysics. 80 years. Think about everything humanity accomplished in that span. We split the atom, decoded the structure of the molecule that carries our heredity, built machines that think, walked on the moon, sent probes past the outermost planets and into interstellar space. And through all of it, we could not fully explain why the atmosphere of our own sun, the nearest star, the one we depend on for every heartbeat of life on this planet, is hundreds of times hotter than its surface. The answer was, quite literally, hanging in the sky over our heads the whole time, and we could not read it. Now, when you hear a mystery like this, there is a temptation to imagine that the laws of physics themselves are broken, that the sun is doing something magical, something outside the rules. It is not. The rule you know, that heat flows outward and cools with distance, is still true. Nothing about the sun overturns thermodynamics. What the coronal heating problem tells us is not that the rule is wrong, but that something else is going on. Something is reaching up past the surface and pouring a tremendous amount of extra energy directly into that thin outer atmosphere, heating it from within by some hidden mechanism that has nothing to do with simply sitting near the warm surface. The heat of the corona is not leftover warmth from the photosphere below. It is being generated up there, delivered up there, by a process we could see the results of for 80 years without being able to watch it happen. And that is the crux of it. We could see the corona was impossibly hot. We could measure it. We simply could not get close enough to catch the mechanism in the act. Everything we knew from a distance, from telescopes pointed at the sun from tens of millions of miles away, watching the outside of a process whose engine was hidden inside. It was a little like trying to understand how a heart works by pressing your ear to someone's chest from across a crowded room. You can tell there is a beat. You cannot see the muscle move. There were candidate explanations, of course. Physicists are not short on ideas. Some suspected the answer lay in the sun's magnetic field, in the way those field lines could snap and reconnect, releasing bursts of energy like a rubber band breaking, depositing heat into the surrounding gas. Others thought the culprit was waves, vast magnetic waves rising up from the churning surface of the sun, carrying energy upward and dumping it into the corona as they broke, the way ocean waves carry energy across a sea and release it all at once against a beach. And in more recent years, a stranger candidate appeared. something we will come back to later in this story, a kind of sudden kink or reversal in the sun's magnetic field that seemed to appear far more often than anyone expected. Each of these ideas had support. None of them could be confirmed, because confirming any of them would require doing the one thing everyone agreed was impossible. It would require going there. It would require flying a machine into the corona itself, into the very place the heating was happening, and measuring it from the inside. So the coronal heating problem was not just a scientific curiosity, a puzzle for specialists to argue about at conferences. It was, in a sense, a challenge written across the sky. The sun was keeping a secret in plain view, a secret about the most fundamental thing there is, energy and heat and the behavior of matter, and the only way to pry it loose was to reach into the fire. And I want to leave you, before we go on, with the part of this that I find genuinely difficult to shake. The sun is not some distant exotic object. It is the most familiar thing in your sky. You have seen it every single day of your life. If someone stopped you on the street and asked you to name something in the heavens you understood, something you were sure about, you might well name the sun. It rises, it sets, it warms your face, it feels known. And yet, for 80 years, this most familiar of all objects hid a mystery so basic, so tied to the simplest rule of heat, that we could not solve it with all the cleverness of the modern age. The thing we thought we understood best, we barely understood at all. Which raises a quiet, uncomfortable question that will follow us through the rest of this story. If we could be this wrong, for this long, about the sun, what else that we take for granted have we never actually explained? Let me try to give you a fuller sense of just how strange this really is, because it is easy to hear a number like 300 times hotter and let it slide past without feeling the weight of it. Imagine you are warming your hands over a stove. The burner glows, and the air just above it is hot, and as you lift your hands higher, the warmth fades, gently, exactly as it should. Now imagine that instead of fading, the air a foot above the burner was suddenly hotter than the burner itself, and a foot above that hotter still, and that if you kept raising your hands, the air kept getting hotter the higher you went, climbing past anything the burner could ever produce, until the air near the ceiling was hundreds of times more scorching than the flame on the stove. You would stop and stare. You would know immediately that something was profoundly wrong with your picture of how heat works, that some hidden source of energy had to be pouring into that upper air, because heat does not simply appear out of nowhere in the cold spaces above a fire. That is precisely the situation the sun presents us with, and it has presented it to us in plain view for as long as we have been able to measure temperatures at all. The mystery is older than most people realize, and the way we discovered it is itself a small story worth telling. For a long time, no one even suspected a problem, because no one knew how hot the corona was. It was just that faint halo seen during eclipses, assumed to be some outer wisp of the sun, presumably cooler than the surface, as any sensible outer layer should be. Then, in the late 1800s and into the early 20th century, astronomers studying the light of the corona during eclipses found something they could not explain. The corona's light contained the signatures of certain colours, certain spectral lines, that did not match any known element. For a while, some believed a brand new element had been discovered up there in the sun's atmosphere, something not found on Earth, and they even gave it a tentative name. But the truth, when it finally came out in the 1930s and 40s, was stranger than a new element. Those mysterious spectral lines were produced by ordinary elements like iron, but iron in a state so extreme, so violently stripped of its electrons, that it could only exist at temperatures of 1,000,000 degrees or more. The corona was not cool. It was staggeringly, impossibly hot, far hotter than the surface beneath it. The signatures in that ghostly eclipse light were the first hint that our star was breaking the campfire rule, and physicists have been wrestling with the implications ever since. And here is what makes it more than a puzzle for specialists, more than an academic curiosity to be filed away. The heat of the corona is not idle. It is the engine of everything the sun does to us. It is because the corona is so unbelievably hot that it cannot stay put, that it boils off into the solar wind, that it drives the storms and the eruptions that can threaten our world. If we do not understand why the corona is so hot, then at the deepest level we do not understand where the solar wind comes from, or what powers the storms, or why some of those storms are gentle and others are monsters. The coronal heating problem sits underneath all of it, the unsolved foundation beneath every practical question we have about how the sun affects the Earth. To leave it unanswered was to build all of our understanding of space weather on a mystery we could not explain. That is why solving it mattered so much, and why so many careers were spent circling it, and why in the end we were willing to fly a machine into a star to crack it. Now, let us meet the man who first taught us that the sun was stranger than it looked, and who was told in no uncertain terms that he was wrong. Part 4. The man who was told he was wrong. Before we go any further into the machine and its journey, there is a person you need to know about, because this spacecraft carries his name, and that fact alone tells you something remarkable about how important this mission was considered to be. Spacecraft are almost never named after people, and they are essentially never named after people who are still alive to watch them launch. This one was. To understand why, we have to go back to the year 1958, to a young astrophysicist named Eugene Parker, sitting down to write a scientific paper that most of his colleagues would consider simply mistaken. At the time, the prevailing view was that the space between the planets was, for all practical purposes, empty, quiet, still. A hard vacuum with perhaps a few stray particles drifting through it, but nothing you could really call active. The sun sat at the centre, shining, and space around it was thought to be more or less calm. Parker looked at the physics of the sun's hot outer atmosphere, the corona we have just been talking about, and he came to a conclusion that ran against that comfortable picture. He argued that the corona could not simply sit there quietly. It was too hot, too energetic to stay put. He calculated that it must be constantly boiling off, streaming outward, flinging a continuous river of charged particles away from the sun in every direction, out past the planets, filling the entire solar system with a perpetual wind blowing off the star. He called it the solar wind, a steady, ceaseless flow of particles pouring off the sun and washing over everything, including the Earth. It was a bold idea, and it was, as it turned out, exactly right. But that is not how it was received. When Parker submitted his paper to a leading physics journal, it came back to him. The reviewer, a well-respected scientist, was not gentle. The paper, he said in effect, contradicted established physics. It should not be published. This is one of the quiet cruelties of science, and also, at its best, one of its strengths. New ideas are supposed to run a gauntlet. They are supposed to be doubted, challenged, tested against the accumulated wisdom of everyone who came before. Most new ideas that sound too strange are in fact wrong, and the doubt is what protects the whole enterprise from drowning in nonsense. But the very same doubt that protects science can also, on occasion, stand directly in the path of someone who happens to be right. And Eugene Parker was right. He did not give up. He appealed. And here the story turns on a single, crucial human being. The editor of the journal was a man named Subrahmanyan Chandrasekhar, one of the towering figures of 20th century physics, a man who would later win the Nobel Prize for his work on the structure and fate of stars. Chandrasekhar reviewed the situation. He could find no actual error in Parker's mathematics. The reviewer disliked the conclusion, found it too radical, but disliking a conclusion is not the same as finding a mistake in it. And so Chandrasekhar, over the objection, made the decision to publish. The paper went out into the world. 2 years later, it stopped being a theory. Spacecraft sent out into that supposedly empty space carried instruments to measure whatever was actually there. And what they found was a wind, a constant stream of charged particles flowing outward from the sun, exactly as Parker had described it, exactly at the speeds and in the manner his mathematics had predicted. The empty, quiet space between the planets turned out to be nothing of the kind. It was filled, always, with the breath of the sun. Eugene Parker had been right, and the reviewer who told him to withdraw the paper had been wrong, and the difference between those two outcomes had come down, in part, to one editor who chose to trust the mathematics over the discomfort. Over the decades that followed, Parker became one of the most important figures in the entire science of the sun. The solar wind became a foundational concept, woven into everything we understand about how the sun interacts with the planets, with the Earth, with the fragile technologies we would eventually come to depend on. And when, many years later, the space agency finally set out to build a mission that would fly directly into the sun's atmosphere, into the very corona whose restless heat had first led Parker to predict the wind, they made a decision they had never made before in the agency's history. They named the spacecraft after him, after a living man. I want you to picture the day it launched. It was August of the year 2018 at Cape Canaveral in Florida, in the deep dark of very early morning, the hour when rockets are so often sent up. And there, among the crowd gathered to watch, was Eugene Parker himself. He was 91 years old. 60 years earlier, as a young man, he had been told that his idea about the sun was wrong, that it contradicted the established physics of his day, that it should not even be printed. Now he stood on the Florida coast in the middle of the night and watched a rocket carrying his own name and carrying a machine built to fly into the very atmosphere he had reasoned about all those years before, climb up off the earth on a pillar of fire and disappear into the sky. Imagine what that must have been. An old man, near the end of a long life, watching the vindication of his youth lift off the ground and head for the sun. He does not say much. What is there to say? He has spent his whole career being proven slowly, patiently right about the star. And here at last is the proof made physical. A spacecraft with his name on its side thundering upward toward the fire. He first imagined pouring its wind across the solar system. When he was a young man, nobody wanted to publish. The light of the rocket climbs and climbs and finally winks out among the stars, and somewhere above the horizon it is already turning, beginning the long fall inward that will take it 6 years later into the corona. He lived to see it fly, but he did not live to see everything it found. Eugene Parker passed away in the year 2022 at the age of 94. He was gone before that Christmas Eve blackout, gone before the deepest passes, gone before the data came home and began, at last, to answer the questions he had spent his life asking. But he lived long enough. He lived long enough to watch his namesake rise, long enough to know that humanity had finally decided to reach out and touch the star he understood better than almost anyone who had ever lived. There is something almost unbearably fitting about the timing of a life like that, a life measured out against the slow, grinding vindication of a single idea, arriving just in time to see that idea carried up into the sky and gone. And that detail, the naming, the old man on the coast at 91, matters for a reason beyond sentiment. It tells you exactly how significant the world of science considered this mission to be, even before it had accomplished anything at all. You do not break a decades-long tradition. You do not put a living person's name on the side of a spacecraft for an ordinary mission. You do it when you believe you're about to do something that will be remembered. They believed it. And to understand why they were right to believe it, we have to look now at the danger. Because the sun that Parker taught us to see, the sun with a wind pouring off of it, is not only a wonder, it is, in a very real and modern sense, a threat. I find myself dwelling on what those 2 years must have felt like for Parker, between the publication of his rejected and rescued paper and the moment the spacecraft measurements confirmed him. To have an idea, to work it out carefully, to be told by respected people that it contradicts established physics and should not see the light of day, and then to have it printed anyway over their objections, and then to wait, knowing that reality itself would soon deliver the verdict. Either the instruments would find his wind, or they would find the empty, quiet space his critics expected, and there would be no arguing with the answer. That is a peculiar kind of exposure, to stake a claim about the actual universe, and then wait for the universe to say whether you were right. Most disagreements between people can drag on forever, unresolved, each side clinging to its view. A claim about nature is different. Nature answers, and when the spacecraft flew out into that supposedly empty space and found it full of the sun's wind, blowing exactly as Parker had said, the argument was simply over. He had been right all along, and now there was proof no one could dispute. It says something about the character of science, and about the character of the man, that being doubted did not stop him. The history of discovery is full of moments like this, where the person who turned out to be right was, for a time, dismissed by the very experts whose job it was to judge such things. It is a humbling pattern, and a reason for a certain humility in all of us about the ideas we are currently confident are settled. The reviewers who rejected Parker were not fools. They were applying the best understanding of their day, and the best understanding of their day happened to be incomplete. Parker saw a little further, and paid the ordinary price for seeing further, which is to be told you are wrong by people who cannot yet see what you see. What redeems the story is that the system, in the end, corrected itself. The evidence came in, the truth won, and decades later a grateful science put his name on the side of a spacecraft and sent it to the sun. Now, let us talk about what the sun can actually do to us. Part 5. What the sun can do to us. Most people, if you ask them why the sun is dangerous, will give you the obvious answer: it is hot. And of course, that is true. Get close enough to that 10,000-degree surface with anything made of ordinary matter, and it simply ceases to exist, boiled away into vapor. But the heat, as strange as this sounds, is not really the danger we should be most worried about. At least not the danger that reaches across 93 million miles of space and touches the life you actually live. The real danger is quieter, more invisible, and it begins in that same mysterious corona we have been circling around this whole time. Remember what Eugene Parker realized. The corona is too hot to sit still. It boils off into space, and that boiling is the solar wind, a relentless stream of charged particles blasting outward from the sun in every direction. This is not a gentle breeze. These particles leave the sun at tremendous speeds, somewhere between about 200 and 500 kilometers every second, and in the fastest streams even quicker. They fill the solar system, they wash over the planets, they wash over us. Right now, as you listen to this, the sun is blowing a wind of charged particles across the Earth, and it has been doing so, without pause, for every moment of your entire life. You do not feel it, and there is a reason for that. A reason that turns out to be one of the most important facts about our planet. The Earth has a magnetic field, an invisible shield generated deep in its molten core, reaching out into space and wrapping the whole planet in a protective bubble. When the solar wind arrives, it does not slam directly into the surface where we live. It hits that magnetic shield and for the most part slides around it, deflected and channeled away, like water parting around the bow of a ship. That shield is one of the great unsung reasons life on Earth is possible at all. Without it, the solar wind would have spent billions of years stripping away our atmosphere, particle by particle, the way it likely did to Mars long ago, leaving behind a dry and airless world. But the shield is not perfect, and the sun does not always blow gently. Sometimes the sun does something far more violent than a steady wind. Sometimes it erupts. Vast regions of the sun's atmosphere can suddenly tear loose in an enormous explosion, flinging billions of tons of magnetized plasma out into space in a single convulsion. These are called coronal mass ejections, and when one of them is aimed at the Earth, it comes barreling across the 93 million miles between us, carrying a tangle of magnetic field and charged particles with it. When that storm front reaches our magnetic shield and strikes hard enough, the shield shudders, it compresses, it ripples, and the careful deflection that normally keeps us safe begins to break down. Energy pours into the upper atmosphere. We call the result a geomagnetic storm. At their gentlest, these storms give us something beautiful. The charged particles funnel down toward the magnetic poles and crash into the upper atmosphere, making the air itself glow in curtains of green and red and violet light. That is the aurora, the northern and southern lights, and it is, in a sense, the visible signature of the sun's wind breaking against the Earth's defenses. For most of human history, that shimmering light was the entire consequence of a solar storm as far as people were concerned. Something lovely in the night sky, and nothing more. But we do not live in that world anymore. We have built a civilization that runs on delicate electrical machinery, and that machinery does not care how beautiful the aurora is. A strong enough geomagnetic storm can knock out satellites, the very satellites we rely on for communication, for navigation, for watching the weather, for the timing signals that quietly run the modern world. It can scramble and disable the systems that give us our position on the globe, the ones in your car and your phone that always seem to know exactly where you are. It can disrupt radio communication, black out the signals that aircraft and ships and emergency services depend on, and in the worst cases, it can reach all the way down to the ground and overwhelm the electrical grid itself, the vast network of wires and transformers that carries power into every home and hospital and city on the continent. That last possibility is the one that keeps the people who study this awake at night. A truly powerful solar storm can induce enormous surges of electrical current in long power lines, currents the grid was never designed to handle, currents that can burn out the massive transformers at the heart of the whole system. And those transformers are not something you can run down to a store and replace. They are huge, custom-built, and in short supply. If enough of them failed at once in a single continent-spanning storm, the recovery would not be measured in hours or days. It could be measured in months or even years. Whole regions could be left without reliable power for a length of time that is genuinely difficult to imagine in a world as dependent on electricity as ours. This is not science fiction. We have a historical marker for how bad it could get, an event from long before we had built anything for the sun to break. In the year 1859, a solar storm of extraordinary power struck the Earth. We call it the Carrington event, after the astronomer who watched the flare that caused it. In that era, the most advanced electrical technology on the planet was the telegraph, the network of wires that carried messages in dots and dashes across countries and continents. When the storm hit, the telegraph system convulsed. Sparks leapt from the equipment. Operators received shocks. Some lines failed completely, while others, bizarrely, kept working even after their power was disconnected, running on the electrical current the storm itself was pushing through the wires. The aurora that night was seen far from the poles, glowing over places that never see such things, bright enough in some accounts that people woke and began their morning thinking the sun had risen early. That storm struck a world with almost nothing electrical to damage. A storm of the same size striking today would find a planet wrapped in wires and satellites and delicate machinery from pole to pole, a civilization utterly dependent on exactly the kind of technology that such a storm attacks. The estimates of what it could cost, in money and in disruption, run high enough that they make almost any other natural disaster in history look modest by comparison. So understanding the sun is not an academic exercise, not a matter of idle curiosity about a distant ball of fire. It is about protecting the actual infrastructure that our entire way of life now depends on. And all of it, the wind, the storms, the eruptions, the currents that could one day take down the grid, all of it is born up there in the corona, in that same impossibly hot, still mysterious outer atmosphere that we could only ever study from a distance. Which brings us back to the machine, and to the question that should have made this whole mission impossible. If the corona is dangerous enough to threaten our civilization from 93 million miles away, how could anything we built possibly survive flying directly into it? I want to give you a clearer picture of that protective shield around the Earth, because it is one of the most important and least appreciated facts about our home. Deep inside the Earth, in the outer core, there is an ocean of molten iron, churning slowly as the planet turns, and that churning generates an enormous magnetic field that surrounds the whole world. You have felt a hint of it every time you have watched a compass needle swing to point north. That same field, reaching far out into space, forms a vast teardrop-shaped bubble around the Earth, squashed on the side facing the sun by the pressure of the solar wind, and drawn out into a long tail on the side facing away, like a windsock streaming in a breeze. This bubble is our shelter. It catches the oncoming wind of charged particles and steers most of them around us, so that they slide past and continue on into space, instead of raining down on the world where we live. We have a grim example of what happens to a world without such a shelter, and it is our neighbour, Mars. Mars once had a thicker atmosphere, and quite possibly rivers and lakes and standing water on its surface. A warmer and wetter world than the cold desert we see today. But Mars is small, and its molten core cooled, and its magnetic field faded away long ago, and once that shield was gone, the solar wind had free rein. Over hundreds of millions of years, the sun's wind stripped the Martian atmosphere away, particle by particle, tearing it off into space until the planet was left thin-aired and frozen, and as far as we can tell, dead. That is the fate the Earth's magnetic field has spared us. When you look up at the sun and feel its warmth, remember that the same star sends a wind that could have done to us what it did to Mars, and that we are protected only by an invisible magnetic bubble, generated by the molten iron turning at the centre of our world. Even with that shield, the stronger storms leave their mark, and we have watched them do it in modern times. In the year 1989, a powerful geomagnetic storm struck the Earth and induced surging currents in the power grid of Quebec, in Canada. In the space of about 90 seconds, the entire grid collapsed. Millions of people lost power in the depth of a northern winter, plunged into darkness and cold in a matter of a minute and a half, all because of a storm born in the atmosphere of the sun, 93 million miles away. That was not the Carrington event. That was not the worst the sun can do. That was a storm well short of the historical monsters, striking a grid that was, by the standards of what could happen, only lightly touched, and still it took down the power for an entire region in a minute and a half. It is a small, sharp reminder that the threat we're talking about is not theoretical, not a distant maybe. The sun has already reached down and switched off the lights for millions of people, within living memory, and it can do far worse. And this is the deep reason the danger keeps growing rather than shrinking. Every year our civilization becomes more electrified, more connected, more dependent on exactly the kinds of delicate systems that a solar storm attacks. The satellites multiply overhead. The power grids grow larger and more interconnected, so that a failure in one place can cascade into others. The timing signals from navigation satellites quietly work their way into more and more of the machinery of daily life, into financial systems and communications and transportation in ways most people never see. We have built a world that is more capable and more comfortable than any before it, and also, in this one particular way, more fragile, more exposed to the moods of the star we orbit. The better our technology becomes, the more we have to lose to a bad day on the sun. Which is exactly why understanding the corona, the birthplace of every storm, stopped being a luxury and became something close to a necessity. Now, let us look at the trick, the beautiful, almost unbelievable trick, that let a spacecraft the size of a car live inside the atmosphere of a star. Part 6. How to survive 1,000,000 degrees. Here is the engineering problem that kept scientists and engineers awake at night for decades. The problem that made this mission sound, for the longest time, like a fantasy. How do you build a machine that can function inside the atmosphere of a star? The sun-facing surface of this spacecraft reaches temperatures of around 2,500 degrees Fahrenheit during its close passes. Let that number settle. That is hotter than lava. That is hot enough to melt steel, to melt aluminum, to melt titanium, to melt very nearly every metal you could name and reach for. And yet, just behind the shield that faces the sun, the scientific instruments, the delicate cameras and sensors that are the entire point of the mission, sit at roughly 85 degrees Fahrenheit. Room temperature. The temperature of a pleasant afternoon. On one side of a barrier, a heat that would destroy almost any material humans have ever worked with. On the other side, close enough to touch, the mild comfort of a spring day. And the barrier between them is only about 4.5 inches thick. We will come to that barrier, that remarkable shield, in a moment. But first I have to untangle something, because there is a contradiction sitting in the middle of this story that most people never get explained to them, and until you understand it, none of this makes sense. I have told you the corona reaches temperatures of 1 to 3 million degrees. I have also told you the spacecraft flies straight through it and does not vaporize. Those two facts seem to be in flat contradiction. If the corona is 1,000,000 degrees, how does anything survive inside it, no matter how good the shield? The answer is one of the most beautiful and counterintuitive ideas in all of physics, and once you see it, you will never think about heat quite the same way again. The secret is this. Temperature and heat are not the same thing. We use the words as if they mean the same idea, but they do not, and the difference is everything here. Temperature is a measure of how fast the individual particles in something are moving. When we say the corona is at 1,000,000 degrees, we are saying that the individual particles of plasma out there are moving with staggering, ferocious energy, zipping around at tremendous speeds. That is a real and true statement about how fast each particle is going. But heat, the actual heat that would damage a spacecraft or burn your hand, is something different. Heat is about how much energy those particles actually transfer to an object when they collide with it. And that depends not just on how fast each particle is moving, but on how many of them there are to do the colliding. This is the piece everyone misses. The corona is unimaginably hot in terms of temperature, but it is also almost a perfect vacuum. It is thin beyond anything in your experience, emptier than the best vacuum ever created in a laboratory on Earth. There are very, very few particles out there per unit of space. So while each individual particle in the corona is screaming along with 1,000,000 degrees of energy, there are so staggeringly few of them that the total amount of heat they can actually deliver to the spacecraft, the sum of all those tiny collisions, stays manageable. Let me try to make that real for you. Imagine standing in an ordinary oven heated to 500 degrees. You would be burned very quickly because the oven is full of air, packed with countless particles all at 500 degrees, and they are constantly striking your skin, all of them, delivering their heat to you in an unrelenting flood. Now imagine a different situation. Imagine a place where the temperature is 100 times higher, but there is almost nothing there, just a scattering of particles so few and so far apart that only a handful strike you each second. Each one that hits you carries enormous energy, yes, but there are so few of them that you barely warm up at all. You could survive in that hotter place far more easily than in the cooler oven, because the oven, though cooler, is dense, and the hotter place is nearly empty. That is the corona. That is why the spacecraft lives. It is not swimming through a million-degree bath, being cooked from all sides by a dense sea of heat. It is passing through a million-degree near vacuum, where the particles are furiously hot but almost absent, a place where the temperature is astronomical, and the actual heat delivered is something a well-designed shield can handle. The number that sounds like instant death, 1 million degrees, turns out to describe a place emptier and, in the way that matters for survival, gentler than a kitchen oven. I want to take you there for a moment, into that strange place, because I think you have to feel it to believe it. Imagine you are standing in the corona, suspended in the sun's outer atmosphere. All around you the instruments read more than 1 million degrees, a temperature so far beyond anything on Earth that the word barely applies. And yet you're not instantly consumed. You look around, and there is almost nothing there. The space between the particles is vast and dark. Now and then, one of them comes screaming past and strikes you, carrying its furious sliver of 1 million degrees, and then it is gone, and there is emptiness again, and a long pause, and then another. It is nothing like standing near a fire where the heat presses against you from every direction all at once, a continuous wall of warmth. Here the heat comes in rare, ferocious pinpricks, each one blistering and each one alone, scattered across an emptiness so complete that the total, minute by minute, is something a body, or a machine, could endure. You're standing inside the hottest thing you will ever encounter, and it is also one of the emptiest, and those two truths together are the reason you are still alive to notice them. That distinction, between the speed of a few particles and the total heat they deliver, is not just a trick of the sun. It quietly governs a great deal of the world. It is why a spark from a fire can land on your skin and merely sting, while a much cooler pot of boiling water would scald you badly, because the spark is tiny and the water is dense. It is why the near vacuum of space, filled though it is with fast-moving particles and radiation, does not simply incinerate an astronaut on a spacewalk. The universe is full of places that are technically ferociously hot, and yet deliver almost no heat, because heat was never only about temperature. It was always about temperature and density together, and we simply never had to learn the difference, because here on the crowded surface of the Earth, where the air is thick and every hot thing is dense with particles, the difference almost never comes up. Now, all of that explains why the corona itself does not destroy the spacecraft. But there is still that other number, the 2,500 degrees on the sun-facing side of the shield, and that heat is very real, because it comes not from the thin corona, but from the raw, blinding sunlight, the concentrated radiance of being closer to the sun than anything has ever been. Against that, the spacecraft needed a shield, and the shield it got is one of the most elegant pieces of engineering the space agency has ever produced. It is called the Thermal Protection System, and at its heart it is deceptively simple. It is made of 2 panels of a material called carbon-carbon composite, an extraordinarily tough, heat-resistant substance, and sandwiched between those 2 panels is a core of carbon foam. And here is the beautiful part. That foam is about 97% air. It is almost nothing. It is one of the lightest solid materials you can imagine, mostly empty space held together by a delicate lattice of carbon. And precisely because it is mostly empty, it is one of the most effective thermal insulators ever flown into space. Heat struggles to cross it because there is so little material for the heat to travel through. The same emptiness that makes the corona survivable is, in a sense, built right into the shield. On the sun-facing side, the shield is coated with a specially made white ceramic paint, and that coating does something clever too. Rather than absorbing the incoming sunlight, it reflects the majority of it straight back out into space, refusing the heat before it can even take hold, and so the whole system works together. The reflective coating turns away most of the light. The nearly empty foam refuses to let what remains cross to the other side, and 4.5 inches behind a face glowing at 2,500 degrees, the instruments sit in the mild calm of an ordinary room, doing their delicate work as if nothing at all were happening just beyond the wall. There was one more problem, one that almost no one ever talks about, and I find it quietly wonderful. At 430,000 miles per hour, the forces trying to tear the spacecraft apart are immense, and the extreme uneven heating stresses the whole structure in ways that could crack it. So the engineers built the frame with flexible joints, deliberately allowing the spacecraft to flex and bend in response to those forces, rather than standing rigid against them and snapping. They designed it, in other words, to bend so that it would not break. There is something almost like wisdom in that, a machine built to survive the most extreme environment we have ever sent anything into, not by being unbreakably stiff, but by being willing to give. I want to linger on the heat shield a little longer, because the more you understand about it, the more remarkable it becomes. It is only about 8 feet across, a disc not much wider than a car is long, and yet everything about the mission depends on it holding perfectly. Behind it, the entire spacecraft has to hide, tucked completely within the shield's shadow, because anything that pokes out into the direct sunlight at that distance would be destroyed. The spacecraft flies, in effect, cowering behind its shield, keeping the disc pointed with great precision at the sun at all times, sheltering its delicate body in the cone of shadow the shield casts behind it. If the spacecraft ever lost that careful orientation, if it turned even slightly so that the sun's light spilled around the edge of the shield and struck the body behind it, the instruments would be exposed to the full ferocity of the close sun, and the mission would end in seconds. So the spacecraft carries sensors along its edges that constantly watch for the first stray touch of direct sunlight, and if any is detected, the spacecraft automatically turns itself back into the safety of the shadow, correcting its posture without waiting for any command from Earth. It has to. At that distance, in the blackout, there is no time to ask for help. Consider, too, what it takes to test something like this before you ever fly it. You cannot exactly build a small sun in a laboratory and throw your spacecraft into it. The engineers had to recreate as best they could the punishing conditions of the close sun here on Earth, using giant furnaces and concentrated banks of lamps and specialized ovens, subjecting the materials to temperatures and stresses meant to mimic what the shield would face, over and over, refining the design until they trusted it. And all of this was in service of a single, almost paradoxical goal, to keep a set of ordinary scientific instruments at ordinary room temperature, while the face of the shield just in front of them glowed at 2,500 degrees. When you hold those two numbers next to each other, 2,500 degrees on one side and a comfortable 85 degrees on the other, separated by 4.5 inches, you begin to appreciate that this shield is not merely a piece of hardware. It is one of the finest pieces of insulation ever created by human beings, a triumph of materials science quietly doing the most extreme temperature management job ever attempted. And I keep returning in my mind to the deeper lesson hiding inside the whole design, the thing that makes this shield almost philosophical. The two great tricks that let the spacecraft survive both come down to emptiness. The corona is survivable because it is nearly empty, a near vacuum whose furious particles are too sparse to deliver much heat. And the shield works because its core is nearly empty too, a carbon foam that is 97% air, so devoid of solid material that heat can barely find a path through it. Emptiness protects the spacecraft from the outside, and emptiness protects it from within. There is something strange and almost beautiful in that. The idea that the way you survive the most extreme environment imaginable is not with more material, more mass, more brute solidity, but with less, with carefully arranged nothingness, with the clever use of empty space. The universe is full of hidden lessons like that, truths that run exactly counter to our instincts. We imagine that survival means armor, means thickness, means standing firm and dense against the danger. And here is a machine that survives the atmosphere of a star by being, in its two most critical parts, mostly empty, and by bending instead of resisting when the forces come. It is worth remembering, when you next assume that strength always means solidity, that the toughest object we ever sent into the fire was hollow at its heart and built to flex. Now, with the shield understood and the paradox resolved, let us follow the long, patient road this machine had to travel just to reach the fire, because you cannot simply point a spacecraft at the sun and fall in. The path there is stranger than you would think. Part 7. The Long Fall Inward. There is something most people assume about a mission to the sun that turns out to be completely wrong. You would think that reaching the sun would be easy. The sun is, after all, the most massive object in the solar system by an overwhelming margin. Its gravity is what holds every planet, every asteroid, every comet in its long looping orbit. It is the great anchor of everything, so surely you would think falling into it would be the simplest thing in the world. You just let go, and the sun's tremendous gravity pulls you in. In truth, reaching the sun is one of the hardest destinations in the entire solar system, and understanding why reveals something surprising about how motion works out there in the dark. The problem is that the Earth, and everything on it, including any spacecraft we launch, is already moving. We are not sitting still relative to the Sun. The Earth is racing around its orbit at an enormous speed, roughly 67,000 miles per hour, carrying all of us sideways around the Sun in a great circle. When you launch a spacecraft from the Earth, it inherits all of that sideways motion. It is already flying around the Sun at 67,000 miles per hour before its engines do anything at all, and that sideways speed is exactly what keeps it from falling in. It is the same reason the Earth itself does not fall into the Sun, despite all that gravity. We are moving sideways fast enough that we perpetually miss. So if you want to actually fall toward the Sun, you cannot simply aim at it and fire your engines. You have to get rid of that sideways speed, that enormous inherited velocity that keeps flinging you around the Sun in a wide, safe circle, and getting rid of it is astonishingly difficult. To cancel out 67,000 miles per hour of sideways motion directly, with rocket engines, would require a staggering, impractical amount of fuel, far more than any spacecraft could ever carry. A direct approach to the Sun, the thing everyone imagines, is essentially impossible. A spacecraft launched from Earth carries too much orbital velocity, and it would simply swing wide, overshoot, and settle into a broad orbit rather than falling inward toward the fire. The solution the engineers used is one of the most elegant tricks in all of spaceflight, and it depends on a planet you might not expect: Venus. Over the course of 6 years, this spacecraft flew past Venus not once but 7 times, and each time it did, it used the planet's gravity as a kind of brake. This is called a gravity assist, and it is a subtle, almost counterintuitive maneuver. As the spacecraft swings past Venus at just the right angle, the planet's gravity tugs on it, and the spacecraft in turn tugs ever so slightly on the planet. In that gravitational handshake, the spacecraft can give up some of its orbital speed to Venus, bleeding off a portion of that stubborn sideways velocity. And every time it shed a little more speed, its orbit around the Sun drew tighter, pulling it closer and closer to the star with each pass. Picture it like slowly reeling in a fishing line. The spacecraft loops around the Sun, comes back around, meets Venus again, sheds a little more speed, and falls a little closer. Loop after loop, year after year, 7 times in all, each encounter with Venus tightening the orbit further, drawing the spacecraft down toward the Sun by careful, patient increments. There was no single dramatic plunge. There was a slow, methodical spiral, a 6-year descent orchestrated with such precision that the spacecraft had to meet a moving planet at a specific point in space, at a specific instant, again and again, each meeting setting up the next. It is one of the most patient journeys ever undertaken, a machine falling toward a star not in a rush, but in a long, deliberate gravitational dance. And here is the thing that I think often gets lost in the story. During those 6 years of tightening orbits, the spacecraft was not simply travelling. It was already working. It was already making discoveries, already sending back things that surprised the scientists who had spent their careers imagining what it might find. Long before that deepest Christmas Eve pass, the mission was rewriting what we knew about the space around the Sun. For one thing, it found that the solar wind near the Sun, the very wind Eugene Parker had predicted, is far more complex and far more turbulent up close than anyone had expected. From a distance from the vantage of the Earth, the solar wind looks relatively smooth, a steady outward flow. But near its source, near the Sun itself, the spacecraft found a churning, chaotic, restless environment, full of structure and violence that had been invisible from far away. It was like discovering that a river which looks calm and even from a bridge high above is, down at the waterline, a roaring chaos of currents and eddies and turbulence. And then there was the strangest discovery of all, one that would turn out to matter enormously for the deepest mystery of the Sun. As the spacecraft flew through the near-Sun environment, it detected sudden, sharp reversals in the Sun's magnetic field. The magnetic field out there, instead of pointing steadily in one direction, would abruptly kink and flip, doubling back on itself in a sharp S-shaped bend, and then snap back to its original direction, all in a matter of seconds. Scientists nicknamed these sudden magnetic reversals switchbacks, after the sharp, doubling turns of a mountain road, and they appeared in far, far greater numbers than anyone had predicted. The near-Sun space was full of them, a constant procession of these magnetic kinks flying past the spacecraft. Nobody had expected so many. Nobody was entirely sure what they were, where exactly they came from, or what they meant. But there was a growing suspicion, even then, that these switchbacks were not just a curiosity. There were hints that they played a key role in accelerating solar particles to remarkable speeds, and perhaps, just perhaps, that they were connected to the great unsolved mystery of why the corona is so impossibly hot. We will come back to the switchbacks, because they become important later. For now, simply hold on to them. Sharp reversals in the sun's magnetic field, far more common than anyone thought, hiding some secret about how the sun works. The spacecraft also did something no machine had ever done. It flew directly through enormous coronal mass ejections, those violent eruptions of billions of tons of plasma we talked about, the storms that can threaten the Earth. But instead of watching them from a distance as we always had before, it flew through them from the inside and measured them as they happened, from within the explosion itself, for the first time in history. Imagine finally being able to fly an instrument into the heart of a hurricane, after a lifetime of only ever watching hurricanes from the shore. That is what this spacecraft did with the storms of the sun. All of this, remember, was happening during the approach, during the 6 years of tightening loops before the mission had even reached its closest and most extreme passes. The discoveries were already piling up. The near-sun environment was already turning out to be stranger and more turbulent, and more full of unexpected structure than anyone had dared to guess. And with each orbit, the spacecraft fell closer, its record for the closest approach broken again and again, each pass carrying it nearer to the fire than any object in the history of the world had ever been. The final flyby of Venus came in November of the year 2024. That last gravitational handshake set up everything. It bent the spacecraft's path one final time, aiming it for the deepest, fastest, most dangerous pass of the entire mission. After that 7th encounter with Venus, there was nothing left to do. No more maneuvers, no more slingshots, no more careful shedding of speed. The spacecraft was on its final trajectory, falling toward a rendezvous with the corona that would take it 3.8 million miles from the surface of the Sun at 430,000 miles per hour. All the years of patience had come down to this. There was nothing left but to wait for Christmas Eve. There is a beautiful subtlety in how a gravity assist actually works that is worth pausing on, because at first it sounds like getting something for nothing. How can simply flying past a planet change your speed when the planet never touches you and you burn no fuel to do it? The answer is that the planet does touch you, in a sense through gravity, and that the exchange is real. As the spacecraft falls toward Venus, Venus's gravity pulls it in and swings it around, and in the process the spacecraft and the planet trade a tiny amount of momentum between them. If you fly past on the correct side at the correct angle, you come away moving more slowly around the Sun than you were before, having handed off a sliver of your speed to the planet. Venus, being unimaginably more massive than a small spacecraft, is slowed by an amount so infinitesimally tiny that it will never be measured, its orbit shifted by less than the width of an atom over the age of the universe. But for the little spacecraft, that same exchange is enormous, enough to reshape its entire path around the Sun. It is a way of borrowing a planet's motion, of using the gravity of worlds as a set of brakes and levers, steering yourself through the solar system by the careful theft of momentum from things far larger than yourself. 6 years of this. 7 encounters with Venus, each one demanding that the spacecraft arrive at exactly the right point in space, at exactly the right instant to meet a moving planet and make the exchange. Miss the timing by too much, and the whole carefully constructed descent could go wrong. It is a testament to how precisely we understand the motions of the planets, how exactly we can predict where Venus will be years in advance, that such a thing is even possible. The engineers were essentially playing a 6-year game of cosmic billiards, calling every shot in advance, each carom off Venus setting up the next, the whole sequence plotted out before the spacecraft ever left the Earth. And the target of that long game was not a place you could see or aim at directly, but a specific ever-tightening orbit that would carry the spacecraft on its final approach closer to the Sun than anything had ever been. It is worth dwelling too on what it means that the spacecraft was already breaking records and making discoveries during all those years of approach, because it reframes the whole mission. We tend to think of a journey as the boring part, the empty travel time before the real event, the way a long drive is just something to endure before you arrive at the destination. This journey was nothing of the kind. Every tightening orbit carried the spacecraft into territory no machine had ever visited, and at each new closest approach it was already the closest any human-made object had ever come to the Sun, already setting a record, already sending back measurements from a place we had never sampled before. The mission did not have a single dramatic moment of arrival preceded by 6 years of nothing. It had 6 years of continuous, escalating discovery, each pass deeper than the last, the switchbacks and the turbulent wind and the coronal mass ejections measured from inside, all of it accumulating, all of it building toward the deepest passes still to come. The falling itself was the science. The long descent was never a prelude. It was the mission, unfolding one tightening loop at a time. Now, let us go to the edge of that final plunge and stand in the room where they waited for it. Part 8. The Plunge. On the morning of the 24th of December, in the year 2024, the team at the Johns Hopkins Applied Physics Laboratory in Maryland was not thinking about the holiday. They were sitting at their consoles, in a room lit by the glow of their screens, watching telemetry, watching numbers, watching a spacecraft they could no longer help do the most dangerous thing it would ever do. This was the moment the entire mission had been built toward. Every design choice, every gram of that carbon shield, every one of the 7 flybys of Venus, every year of patience, all of it had led to this single pass, and now it was here, and there was nothing left to do but watch it happen and hope. Let me take you into that room, because I think it is one of the quietly extraordinary moments in the history of exploration, and almost no one witnessed it. There is no crowd cheering. There is no dramatic countdown. There are only engineers and scientists at their stations, people who have given a decade of their working lives to this one machine, sitting in the artificial calm of a control room while tens of millions of miles away, their spacecraft falls toward a star. On the screens, the numbers describe the descent, the distance to the Sun shrinking, the speed climbing, 3.8 million miles from the surface, 430,000 miles per hour, numbers that no human-made object had ever reached, ticking past on a display as calmly as a clock, and then, exactly as they had always known it would, the signal begins to fade. As the spacecraft drops deeper toward the Sun, it enters the communications blackout, that region so close to the star that the raging electromagnetic radiation of the corona completely overwhelms any signal the spacecraft can send. The connection thins, the stream of data grows ragged, then sparse, then stops, and the room goes quiet in a different way than before, a heavier way, because now the screens have nothing left to tell them. The spacecraft is gone. Not destroyed, they hope, but gone from their reach, dropped behind a wall of solar fury, flying on nothing but its own preloaded instructions, unable to hear a single command, unable to send a single word. A machine they spent more than a decade designing and building and nursing through 6 years of ever-tightening orbits has just vanished into the atmosphere of a star, and there is no way, none at all, to know if it is still alive. Now imagine being the spacecraft. Imagine what is happening out there, in the silence, where no human eye can follow. It is falling toward the Sun faster than anything has ever moved, 430,000 miles per hour, fast enough to cross an entire continent in the time it takes to draw a breath. Ahead of it, filling the whole sky, is the Sun, no longer a distant disk but an overwhelming, blinding wall of light and fire, closer than any object has ever come and lived. The shield on its sun-facing side is glowing now, climbing toward 2,500 degrees, hotter than lava, the specially made white coating reflecting away what light it can while the nearly empty carbon foam behind it holds the line. And all around the spacecraft is the corona, the Sun's own atmosphere, 1,000,000 degrees and more, a place no machine has ever been this deep inside. The particles come screaming past, ferociously hot and mercifully sparse, striking the shield in rare, blistering pinpricks scattered across the emptiness. The whole frame flexes and bends under the immense forces, giving rather than snapping, exactly as it was built to do. And through it all, the little machine keeps working, its instruments recording, its cameras watching, its systems holding steady, entirely alone, entirely out of contact, doing the one thing it was made for in the one place it was made to go. Nobody sees it. That is the strange, almost unbearable part. The greatest, most dangerous moment of the entire mission happens in total darkness, unwitnessed, unrecorded in real time by any human being. The spacecraft makes its closest approach, sweeps through the corona at its record distance and record speed, endures the full fury of the sun, and does all of it in silence, while back on Earth the people who love it, and I do not think that word is too strong, sit in a quiet room and wait, with no way of knowing whether it has already been torn apart or is sailing through exactly as they designed it to. Think about the distances involved, to feel how alone it truly was. Mercury, the innermost planet, the closest world to the Sun, never comes within 28 million miles of the solar surface. This spacecraft was 3.8 million miles away, more than 7 times closer than Mercury has ever been. It had gone somewhere no planet goes, into a region of space that had, until that moment, belonged entirely to the Sun. And it went there not with a crew, not with anyone to make decisions in the moment, but on its own, following instructions written and loaded long before, trusting its shield and its design, and the calculations of the people who built it. The waiting was the hardest part, and it did not end quickly. The blackout was not a matter of minutes. The team had to sit with the silence for the better part of 2 days, through Christmas Eve and into the days after, not knowing. Consider what that must have been like. To have poured your career into a single machine, to have watched it fly for 6 years toward this exact moment, and then to have it disappear into a star during the holidays, and to be able to do nothing but wait and hope and try to trust the work you had done. There is a particular kind of courage in building something and then letting it go somewhere you cannot follow, somewhere you cannot help it, somewhere you can only find out afterward whether it lived or died. The engineers had that courage forced upon them, and they sat in it through the silence and waited. And I want to leave the tension exactly here, unresolved, the way they had to live it. The spacecraft is out there, right now in the story, somewhere inside the corona, out of contact, its fate unknown. The screens are dark of any word from it. The room is quiet. It is Christmas Eve, and the most audacious thing our species has ever attempted is happening in a silence so complete that no one on Earth can say whether it is a triumph or a tragedy. The team has done everything they can do. Every choice has already been made. Every safeguard is already in place. There is nothing left but the waiting, and the hope, and the slow passage of hours while a machine flies alone through the fire of a star and cannot tell them how it fares. For thousands of years, every culture that ever looked up treated the sun as something beyond reach, a god, a mystery, a power that could be worshipped and feared but never approached. And here, in a quiet room in Maryland, in the last days of the year 2024, a group of people sat and waited to learn whether the thing they had sent to touch it had survived the touching. They had reached for the untouchable. Now they had to wait to find out what the untouchable would do to the thing that reached. There is a strange loneliness to autonomy at that distance that I think we rarely appreciate. We're used to the idea that our machines in space are guided, that there is a room full of people watching over them, ready to send a command if something goes wrong. And for most of a mission that is true. But here, in the deepest part of the past, that safety net simply did not exist. Even if the team had seen a problem, even if they had known in that moment that something was failing, they could have done nothing, because no signal could reach the spacecraft through the blackout, and even outside the blackout, the sheer distance meant that any command would take many minutes to arrive. The spacecraft was, for those hours, entirely its own keeper. Every decision it might need to make, every correction, every response to danger, had to come from the instructions already written into it, and from its own automatic systems, watching their own edges, holding their own course. It was as alone as anything we have ever built, trusted completely to fend for itself in the most hostile place we have ever sent a machine. And it did fend for itself. Somewhere in that silence, at the very bottom of its fall, the spacecraft reached the closest point of its entire journey, swept through the corona at its record distance and record speed, endured the full weight of the close sun, and began the long climb back out, all of it on its own, all of it unwitnessed, all of it exactly as it had been built to do. The most extreme moment in the history of human exploration happened with no one watching, no cheering, no live feed, no triumphant broadcast, just a small machine doing an impossible thing in the dark, faithfully, alone, while the people who made it sat millions of miles away and could only wait to learn, afterward, whether their trust had been rewarded. Now, let us wait with them and let us find out what came back across the silence. Part 9. I Am Here. The silence lasted through Christmas Eve, through Christmas Day, into the day after. 2 days of not knowing. And then, on the evening of the 26th of December, the waiting ended. Across all those millions of miles out of the fury and the radiation and the blackout, a signal reached the Earth. It was not much. It was not a flood of data, not a triumphant transmission of everything the spacecraft had seen. It was a single, simple tone, a beacon, a prearranged radio signal that carried, in its way, only one piece of information, the most important piece there could possibly be. It said, in effect, I am here, I am operational, everything is working normally, that was all, and it was everything. Picture the room now. For 2 days it has been quiet, heavy with a tension no one quite says out loud. People have gone home and come back, slept badly, checked and rechecked, waited. And then the beacon comes in, that small tone from a machine that flew into a star, and in an instant the 2 days of the held breath break open. The room, by every account, erupted. Engineers who had spent years of their careers, in some cases the better part of their working lives, on this single mission, were openly emotional. There were people in that room who had helped design the shield, who had planned the Venus flybys, who had argued over trajectories and tolerances and the exact thickness of the carbon foam, and now, after everything, they had their answer. The spacecraft had flown into the atmosphere of the Sun, closer and faster than anything human hands had ever built, and it had come through. It was alive. It was working. It was on the far side of the impossible, and it was fine. I think it is worth pausing here on the human size of that moment, because we talk so easily about missions and spacecraft and data that we can forget there are people underneath all of it. These are men and women who chose to spend their one finite professional life on a single, uncertain thing. When they started, they did not know if it would work. Plenty of experts had said it could not. They committed anyway. They gave it their years, their expertise, their nights and their worry, with no guarantee that any of it would amount to more than a very expensive failure falling into the Sun. And then they had to watch it disappear into a 2-day silence during the holidays, unable to help, unable to know. When that beacon finally came, it was not just data confirming a spacecraft's health. It was the answer to a question they had been carrying quietly for years. Was it worth it? Did the thing we gave our lives to actually work? And the Sun, at last, through that little tone, told them yes. Remember the silence. Remember how heavy it was, how the screens had nothing to say, how a machine they had built and loved had vanished behind a wall of solar fire with no way to call out. That silence had been the shape of all their fear, the container for every doubt about whether the shield would hold and the design would survive and the decade of work would come to anything. And now the silence was broken, not by a torrent, not by a fanfare, but by the smallest possible signal, a single tone that meant the smallest and largest possible thing at once. I am here. The silence that had held all their dread became, in an instant, the silence that made the relief possible, the empty space against which that one small sound could land with the weight of everything they had hoped for. There is something almost poetic about the form the message took. Not a description, not a boast, not a report, just presence. I am here. It is, when you think about it, the oldest and most fundamental message there is, the thing any living creature most wants to be able to say and to hear. I made it. I survived. I am still here. A machine we built flung into the atmosphere of a star, reduced its entire triumph to that one ancient sentence, and sent it home across the dark, and the people who made it wept to hear it. And once they knew it was alive, they knew something else, something that changed everything about what came next. If the spacecraft was healthy, then its instruments had been recording throughout the pass. Its cameras had been watching. Its sensors had been measuring the corona from the inside during those 2 silent days, gathering data of a kind no one had ever possessed. A detailed view of the Sun's atmosphere taken not from a telescope pointed at it, from tens of millions of miles away, but from within it. All of that was sitting in the spacecraft's memory now, safe, waiting. The beacon meant not only that the machine had lived, but that everything it had seen had lived too and would be coming home. The full science data began downloading to the Earth in early January of the year 2025, and as it came in, stream by stream, The researchers finally had in their hands the thing they had been chasing for the entire history of solar science. A view of the sun's corona from the inside. Not an inference, not a model, not a distant photograph, but direct measurement, taken in the place where the great mysteries live, by a machine that had gone there and returned. The waiting was over. The silence was broken. The spacecraft was alive. And now, at last, it was time to find out what it had seen. Because it had seen things no one had ever seen before, and some of them began, almost immediately, to answer questions that had stood open for the better part of a century. It is worth remembering, too, that the beacon was designed to be exactly this simple on purpose. The engineers knew that after such a pass, the very first thing they would need was not a flood of complicated data, but a single, unambiguous answer to the only question that mattered in that moment. Is it alive? So they built in this minimal signal, a plain tone that could be sent with almost no power and received with almost no doubt, carrying just enough information to say that the spacecraft had come through and its systems were healthy. There is a kind of wisdom in that design, an understanding of the human beings on the other end. After 2 days of dread, they did not need to be handed a puzzle to decode. They needed a yes. And so the spacecraft was built to give them a yes, in the clearest form a machine can offer, across all those millions of miles of space. Everything else could come later. The detailed health reports, the full accounting of how every system had fared, the enormous trove of science data waiting in the spacecraft's memory, all of it would follow in the days and weeks ahead. But first, before any of that, the simple tone, the yes, the confirmation that the impossible thing had been survived. It is a small mercy in its way that the first word back from a machine that flew into a star was not a technical report but something close to reassurance, a signal shaped in the end for the people who had been waiting and who needed, more than they needed any measurement, to simply know that it had lived. Now let us look at the first of them and watch, for the first time in human history, the wind of the sun being born. Part 10. Watching the wind be born. For as long as we have known about the solar wind, ever since Eugene Parker first argued that it must exist, we have only ever been able to study it far from its source. We measured it as it passed the Earth, 93 million miles from the Sun. We measured it with spacecraft scattered across the solar system, always at a great distance from where it began. It was a little like knowing a river only by the wide, slow water where it passes through a city, hundreds of miles downstream from the mountains where it is born. You could learn a great deal about the river that way. You could measure its flow, its temperature, its chemistry, but you could never see it begin. You could never stand at the spring where the first water pushes up out of the ground and watch the river come into being. This spacecraft carried a camera, a wide-field imager built specifically for this mission, and during its close passes it did something no instrument had ever done. It watched the solar wind being born. It captured in actual footage the streams of charged plasma pulling away from the corona, tearing loose from the sun's outer atmosphere, accelerating outward, and organizing themselves into the very patterns that would eventually cross the solar system and reach the Earth. For the first time in history, we could see the river at its source. We could watch the wind of the sun in the act of becoming the wind right at the moment it left the star. Let me take you into that footage, because it is one of the most quietly astonishing things this mission gave us. Imagine you're riding along with that camera, deep in the corona, closer to the sun than any planet has ever been. Below you and around you is the sun's outer atmosphere, vast and luminous and restless. And you watch as, out of that churning brightness, the plasma begins to move. Threads of charged particles gather and lift away from the corona, hesitant at first, and then faster, streaming outward, drawing themselves into ribbons and currents, accelerating into the flow that will carry them out past Mercury, past Venus, all the way to the Earth and beyond. You're watching the headwaters of a river that touches every world in the solar system, a river we have swum in our whole lives, 93 million miles downstream without ever once seeing where it starts. And here it is, welling up out of the star in front of you, the exact stuff that will, a few days from now, brush against the magnetic shield of your own planet and paint the polar skies in light. There is a particular kind of wonder in seeing the origin of something familiar. We have always lived inside the solar wind. It has been blowing over the Earth for every moment of your life, for every moment of all life. And yet we had never seen it begin. To finally watch it come loose from the sun, to see the birth of the thing that has surrounded us always, is to have a hidden piece of our own world suddenly made visible. The scientist described it in almost exactly those terms, as finally being able to watch the river at its source after decades of only ever observing it far downstream. The whole set of dynamics that had been invisible, the actual mechanics of how the solar wind forms and organizes and launches itself outward, suddenly became something we could watch happening in front of us. And the footage did more than satisfy our curiosity. It captured something that, until then, had lived only in theory, a phenomenon scientists had predicted but never actually seen. They have taken to calling it the solar wind U-turn, and it is genuinely strange. When the sun launches one of those enormous coronal mass ejections, one of the violent eruptions that fling billions of tons of magnetized plasma out into space, we naturally assume all of that material simply blasts outward, away from the sun, gone. But it turns out that is not the whole story. Some of the ejected material does not escape. Some of it loops back. Caught by the sun's own powerful magnetic field, a portion of the plasma curves around and turns back toward the star, falling inward again, altering the corona as it returns and influencing the path and the shape of the next eruption to come. Think about what that means. The sun is not simply throwing material out into space in one direction. It is in part a system that feeds back on itself, where an eruption sends plasma outward, and some of that plasma comes home, and its return changes what the sun does next. It is less like a cannon firing and more like a great churning tide, where what goes out can come back, and what comes back shapes what goes out again. The spacecraft filmed this directly, up close, in a level of detail no one had ever come near before. We had guessed the U-turn might happen. Now we had watched it happen. And this is not merely a beautiful curiosity, though it is that. Understanding this feedback, understanding that the sun's eruptions can loop back and reshape the conditions for the next eruption, is critical for one of the most practical problems we have, the problem of predicting space weather. Remember the danger we talked about, the geomagnetic storms, the threat to satellites and power grids, the spectre of a Carrington-scale event striking our wired and electrified world. One of the deep difficulties in forecasting solar storms has always been that some are far more powerful than others, and it has been genuinely hard to understand why. If the sun's own ejected plasma can turn around and modify the corona, feeding back into the system that launches the next storm, then that feedback may be part of the answer to why some storms are gentle and others are monsters. Every piece of this we come to understand is a piece we can eventually fold into our ability to see the dangerous storms coming. But I do not want to rush past the sheer strangeness and beauty of what happened here into only the practical payoff, because the practical payoff, real as it is not the whole reason this matters. Step back and consider the arc of it. A young man in 1958 reasons from the physics of the sun's hot atmosphere that there must be a wind pouring off the star. He's told he is wrong. He's proven right. He spends his life becoming one of the great figures of solar science, and near the end of that life he stands on a coast in Florida and watches a spacecraft bearing his name rise into the sky, built to fly into the very atmosphere whose heat first led him to imagine the wind. He does not live to see it arrive, and then, a few years after he is gone, that spacecraft reaches the corona, and its camera looks out, and it sees the wind, his wind, the solar wind, in the very act of being born, pulling away from the sun exactly as he had reasoned it must, more than 60 years earlier, when nobody wanted to believe him. There is a completeness to that, a closing of a circle that stretches across a human lifetime and beyond it. The wind he predicted seen at last at its source by the machine that carries his name. He was not there to watch the footage, but in a sense the footage is the final vindication of everything he argued. The moment his idea stopped being a theory measured at a distance and became something we could watch happening at the star itself. And the seeing of it was only the beginning of what that inside view could do, because the same closeness that let us watch the wind be born also let us begin, for the first time, to crack the oldest and deepest mystery of the sun, the one that had stood unsolved for 80 years, the impossible heat of the corona. There is a phrase the scientists used about this footage that I keep turning over, the idea of finally seeing the source. For all of the history of science, we have been in the position of people studying a river only where it is wide and slow and far from the mountains. We could sample its water, measure its speed, chart its floods, and from all of that we could infer a great deal about where it must have come from and how it must behave near its origin. But inference is not sight. There is a difference between deducing what the headwaters must be like and actually standing at the spring, watching the first water push up out of the rock. For the solar wind, we had spent decades doing the former, building elaborate and clever models of how the wind must form, arguing over the details, testing our guesses against measurements taken far downstream at the Earth. And now, suddenly, we were doing the latter. We were watching it happen. The models could be checked, not against distant echoes, but against the thing itself, caught in the act at its birthplace. That is a rare and precious thing in science, the moment when a phenomenon you have only ever studied indirectly becomes something you can watch directly, and it almost always brings surprises. The near-Sun environment turned out to be more turbulent, more structured, more alive with unexpected detail than the tidy downstream picture had suggested. The smooth, steady wind we knew at the Earth was revealed near its source to be born out of chaos and violence and constant restless motion, gradually organizing itself into the calmer flow that would eventually reach us. It is a bit like discovering that a person you had only ever known as a calm, composed adult had been, in their youth, wild and turbulent and full of storm. The solar wind grows into its steadiness. Near the sun, at its birth, it is anything but calm. And I think it is worth holding on to the sheer intimacy of what this footage represents, because it is easy to let it become just another data set, another achievement to list. This is the birth of the thing that surrounds us. The solar wind is not some remote phenomenon happening far from our lives. It is the medium we live inside, the outermost breath of the sun, blowing over the Earth every second of every day, shaping the space around our planet, driving the auroras, carrying the storms. It has been present for every moment of every life that has ever existed on this world, an invisible constant, as much a part of our environment as the air, though we almost never think of it. And for the first time we watched it come into being. We watched the wind that has always surrounded us pull loose from the star and begin its journey toward us. It is as if you had lived your whole life beside a river without ever seeing its source, and then, one day, you were finally taken to the spring and shown the exact place where the water you had always known first came into the world. There is a kind of homecoming in that, a closing of a distance we had always simply lived with, and it came to us across 93 million miles sent home by a machine flying through the fire. Now, let us look at how, at last, the answer began to come into focus. Part 11. The answer emerging. For more than 80 years, the coronal heating problem stood as one of the great unanswered questions in all of science. Why is the sun's outer atmosphere hundreds of times hotter than its surface? Why does the temperature climb as you move away from the fire, in apparent defiance of the simplest rule of heat you know? We could measure the impossible heat. We could not explain it. And the reason we could not explain it, at the deepest level, was always the same. We could not get close enough to catch the mechanism in the act. Everything we knew from a distance, watching the outside of a process whose engine was hidden inside. Now, at last, we had a machine on the inside, and the answer began, slowly, to come into focus. Let me bring back the switchbacks, because this is where they finally matter. Remember them from the approach, those sudden, sharp reversals in the sun's magnetic field, the places where the field would abruptly kink and double back on itself in an S-shaped bend, and then snap back to its original direction, all in a matter of seconds. Remember that the spacecraft found them in far greater numbers than anyone had predicted, that the near-sun space was full of them, a constant procession of these magnetic kinks. And remember the growing suspicion, even early on, that they were not just a curiosity, that they might be tied to how solar particles get accelerated and perhaps to the great mystery of the corona's heat. The preliminary data from the close approaches has been pointing more and more firmly in exactly that direction. It suggests that those switchbacks, those zigzagging reversals in the magnetic field, are one of the primary mechanisms by which energy is carried from the surface of the sun up into the corona and dumped there as heat, driving the temperature into the millions. The switchbacks appear to be in part the missing hand that reaches up past the surface and pours energy into the thin outer atmosphere, the hidden process that makes the corona break the campfire rule. And crucially, the spacecraft, by flying through them up close, is giving scientists the resolution they need to actually study them, to map how they form and how they behave and how much energy they carry, rather than merely guessing at them from far away. But I want to be honest with you about the shape of this answer, because it is not the clean, single, elegant solution that a lifetime of stories about science might lead you to expect. It is not one equation, one mechanism, one triumphant reveal. The picture emerging from the data is that the heating of the corona is not any single process at all. It is a complex interplay of several processes working together. There are the switchbacks, there is magnetic reconnection, the snapping and reconnecting of magnetic field lines that releases energy in sudden bursts, like a rubber band breaking and dumping its stored tension all at once. There is turbulent wave activity, vast magnetic waves rising off the churning sun and breaking in the corona, depositing their energy the way ocean waves release their power against a shore. The truth seems to be that the corona is heated by a tangled combination of all of these magnetic reconnection and wave turbulence and switchbacks, woven together into a mechanism far richer and more intricate than any single tidy explanation. And I think there is something honest and even beautiful in that. The universe rarely resolves its deepest mysteries into a single sentence. More often, when we finally get close enough to see clearly, we find that the answer is a system, a collaboration of processes, a layered and interlocking complexity that we could only ever have untangled by going there and watching it directly. For 80 years we asked a simple-sounding question: why is the corona so hot? And the answer, it turns out, was never going to be simple. It was going to be a whole choreography of magnetic energy, and the only way to read it was to fly into the middle of the dance. Here is what matters most, though. After 80 years, the answer is finally within reach. This is not a small thing. This is one of the longest-standing open problems in the physics of stars, a mystery that had defeated every generation of solar scientists since before the Second World War, and for the first time we're not merely theorizing about it from a distance. We're measuring it from the inside, with a machine flying through the very region where the heating happens, gathering the resolution and the detail needed to finally map the process properly. 80 years of mystery may be close to having an answer, not a guess, an answer, drawn from direct measurement, taken in the place where the mystery lives. Now, let me bring you all the way back to that campfire. Remember the rule you've known your whole life, the one that seemed so unbreakable. Walk away from a fire and it gets cooler. The closer you are to the source of heat, the hotter you are, and the farther you go, the colder it gets. And remember how the sun seemed to shatter that rule completely, its corona somehow growing hundreds of times hotter as you moved away from the surface, as if you had stepped back from a fireplace and burst into flame. It felt like a violation of physics itself, but it was never a violation. That is the resolution, and it is worth holding on to. The rule about the campfire was always true. Heat does flow outward and cool with distance. Nothing about the sun overturns that. What we were missing was not a flaw in the rule, but a hidden mechanism operating alongside it, a set of processes, switchbacks and reconnection, and turbulent waves, reaching up past the surface and actively pouring fresh energy into the corona, heating it from within rather than letting it merely bask in the warmth radiating up from below. The corona is not hot because it sits near the surface. It is hot because the sun's magnetic field is doing work up there, delivering energy directly into that thin outer atmosphere by mechanisms we simply could not see until we went and looked. The campfire never lied. There was just a second fire, an invisible one, burning in the air above the flames, and we had to fly into the smoke to find it. I find that genuinely moving, and I want to sit with why. The sun is the most familiar object in your entire sky. You have seen it every day of your life. If someone asked you to name something in the heavens you felt sure you understood, you might well name the sun, and yet it kept this secret, this basic secret about heat, the simplest and most everyday physics there is, for 80 years, in plain sight, hanging over the heads of every human being who ever lived. The thing we thought we understood best, we did not understand at all, and it took building a machine, wrapping it in a shield of nearly empty carbon foam, flinging it around Venus 7 times over 6 years, and flying it into the atmosphere of the star itself, just to begin to read what had been written in the sky above us the whole time. That should leave a small vertigo in you, the same one it leaves in me. If we could be this wrong for this long about the sun, the nearest and most familiar star, the one object no human has ever failed to notice, then what else? What other simple, everyday, obvious-seeming things do we walk beneath every day, certain we understand them, when in truth we have never actually explained them at all. The corona's heat was hiding in the open for 80 years. It makes you wonder, gently, how many other secrets are hiding in the open still, waiting for someone to build the machine that can finally go and see. The sun taught us humility in the most direct way possible. It let us think we knew it, for all of human history, and then it made us fly into a star just to learn how its own light stays warm. I want to be careful here not to overstate what has been settled, because honesty is part of what this channel is for, and the coronal heating problem is not yet a closed case. The data is still being analysed, the picture is still coming into focus. What we have is not a final, triumphant proof, but a strong and growing body of evidence pointing toward the switchbacks and reconnection, and wave turbulence as the key players. Scientists are still working to untangle exactly how much of the heating each process contributes, how they interact, how they combine across the vast and varied surface of the sun. The answer is emerging, but emerging is the right word, and it is worth resisting the temptation to declare the mystery solved and move on. What has genuinely changed? What makes this a turning point rather than just another incremental step is that we are no longer working in the dark. For 80 years, the problem was intractable in large part because we could not get close enough to gather the right kind of evidence. Now we can. Now the measurements are coming in, from inside the corona, at the resolution the problem always demanded. The difference between an unsolvable mystery and a hard problem being actively solved is exactly the difference between having no data and having the right data. And this spacecraft moved us across that line. There is a lesson buried in that about how the deepest questions in science tend to actually get answered, and it is not the lesson the popular stories usually tell. We like to imagine the lone genius having a flash of insight, the sudden brilliant idea that dissolves a century of confusion in an afternoon. And sometimes something like that does happen. But far more often, the great old mysteries fall not to a single clever thought, but to a new ability to look, to a new instrument, a new vantage, a new machine that lets us gather evidence we simply could not gather before. The coronal heating problem did not yield to a better equation dreamed up at a desk. It began to yield when we built something that could physically go to the place where the heating happens and measure it directly. Progress so often is not about thinking harder. It is about finding a way to see what was always there but always hidden. The sun had been performing this trick of impossible heat in full view for the entire history of our species, and what finally let us begin to catch it was not a smarter idea about the sun, but the audacity and the engineering to fly straight into it. And that reframes the whole 80 years of failure in a gentler light. It was not that generations of solar scientists were not clever enough, not that they lacked the insight to crack the problem. It was that they were, in a sense, trying to read fine print from across a canyon. No amount of intelligence can substitute for the missing evidence when the thing you need to see is simply too far away to resolve. Those decades of theorizing, of building models and arguing over mechanisms were not wasted. They were the necessary preparation, the careful mapping of what the possible answers might be, so that when the evidence finally arrived, we would know how to read it. The switchbacks meant something to the scientists who saw them precisely because decades of thought had prepared the ground for understanding what they might do. The machine gathered the evidence. The 80 years of human thinking gave us the eyes to interpret it. Neither would have been enough alone. Now, let us come back from the fire and ask the last and largest question. Not how the sun works, but what it means that we reached it at all, and what that reaching may yet do for the fragile world we built in its light. Part 12. Reaching the Untouchable. The spacecraft did not stop after that Christmas Eve pass. Through the whole of the year 2025, it has continued making close approaches, again and again matching its record distance of 3.8 million miles from the surface and its record speed of 430,000 miles per hour, sweeping through the Corona Pass after pass, gathering more of the inside view that no instrument had ever had before. And the timing could hardly be better, because the sun right now is near the peak of its 11-year cycle of activity, the stretch when it is most restless, when solar storms are most frequent and most intense. The sun runs through this rhythm endlessly, growing quiet and then stirring back to violence over roughly 11 years, and the spacecraft has arrived to fly through the corona during one of the stormiest chapters, collecting its data in the thick of the action, exactly when the sun has the most to show. But step back for a moment from the wonder of it, and ask the plain question. Why does this actually matter in practical terms for the life you live? And the answer comes back to the danger we talked about, the threat the sun poses to the fragile electrified civilization we have built. Right now, every time a major solar storm comes barreling toward the Earth, the people who watch for such things get somewhere between 15 minutes and a few hours of warning. That is it. That is all the time we have to react when a monster leaves the sun and heads our way. 15 minutes to a few hours is barely enough time to put some satellites into a protective safe mode, to scramble and brace a few systems. It is nowhere near enough time to truly protect something as vast and slow and complicated as a continental power grid. And we know how bad it could get, because we have the historical marker of the Carrington event, that great storm of 1859 that set telegraph lines sparking in a world with almost nothing electrical to break. A storm of that scale striking today, striking our world of satellites and power lines and delicate machinery wrapped around the planet from pole to pole, could trigger cascading failures in power grids across entire continents. It could burn out the massive transformers at the heart of the electrical system, the ones that are custom-built and in short supply and cannot simply be replaced overnight. Some estimates suggest the recovery could take months, or even years, at a cost that would make almost any other natural disaster in human history look small by comparison. This is not a distant hypothetical. It is a real vulnerability of the actual world you live in, a weakness written into the very infrastructure that carries power into your home. This is where the spacecraft's work stops being only beautiful and becomes, potentially, protective. The data it is gathering near the sun, seeing how the solar wind forms at its source, watching how coronal mass ejections behave when they are born, tracking how the magnetic structures evolve before they ever launch. All of it is the foundation for building genuinely reliable early warning systems. If we can understand the sun's storms at the moment of their birth, if we can read the signs in the corona before the storm has even left the star, then instead of 15 minutes of warning, we could eventually be talking about days instead of minutes. That is not a small improvement. That is the difference between bracing for impact and actually preparing, the difference between watching the grid go down and having the time to protect it. It could mean safeguarding trillions of dollars of infrastructure and, far more importantly, the millions upon millions of people who depend on that infrastructure every single day for their heat, their water, their medicine, their food, their lives. So this is what it comes to in the end. On the 24th of December, in the year 2024, a machine built by human hands flew into the atmosphere of a star. It survived temperatures that would vaporize any ordinary material, protected by a shield of nearly empty carbon foam and the strange grace of a 1,000,000-degree near vacuum that turns out to deliver less heat than a kitchen oven. It moved faster than anything we have ever built, fast enough to cross a continent in 20 seconds. It went more than 7 times closer to the sun than the innermost planet has ever dared. And it came back, alive, carrying data that is already beginning to rewrite the textbooks, already answering an 80-year-old mystery, already laying the groundwork to protect the world from the very star it flew into. Now think about the whole sweep of it, the full length of the human story behind this one small machine. For thousands of years, across every culture that ever raised its eyes, the sun was untouchable. It was a god to be worshipped, a fire to be feared, a mystery to be told stories about, a power that ruled every harvest and every season and every day of every life, and that no one, in their most extravagant dreams, imagined we could ever reach. It was the very definition of the beyond, and within a single human lifetime, within the span of the years that Eugene Parker walked the earth, we went from a young man being told his idea about the sun was too radical to publish, to a spacecraft bearing that same man's name flying directly into the star and sending back its secrets. The untouchable was touched. The thing every ancestor treated as forever out of reach, we reached anyway. I keep coming back to that phrase, touching a star, because when we began this story it sounded almost like a boast, a piece of impossible language, the kind of thing you say for effect. Humanity literally touched a star. It sounds too large to be true, but you have followed the whole of it now. You know about the corona and the campfire rule, about temperature and heat and the near-empty foam, about the 7 passes of Venus and the 2 days of silence and the single small tone that said, "I am here." You know exactly what it took and exactly what it cost and exactly how it was done. And so the phrase has changed its weight. It is not a boast anymore. It is a quiet, earned, astonishing fact We touched a star. We built a thing that flew into the sun and came home, and the sentence that sounded impossible at the start is simply, plainly, true. And here, at the very end, is the part I find most difficult to shake, the part that stays with me after all the numbers and all the engineering. The most disturbing thing this mission revealed was not that the sun is dangerous, though it is. It was not the threat of the storms or the fragility of the grid, real as those are. The most disturbing thing is quieter than that. It is that the closest star to us, the one we depend on for every heartbeat of every living thing on this planet, the most familiar object in the entire sky, kept a fundamental secret from us for 80 years, hidden in the open, in plain view, above the head of every person who ever lived. We thought we knew the sun. We did not. We had to fly into it, into the fire itself, just to begin to read what it had been telling us all along. There is a strange humility in that, and a strange wonder too held together in the same thought. We are small enough to have missed the obvious for 80 years, and we are large enough to have built a machine that could reach into a star to find it. Both of those things are true at once, and the sun, patient and burning and 93 million miles away, taught us both of them in the same lesson. If you sit quietly with the whole of it, there is a symmetry that I find almost impossible to look away from. The sun gave us life. Every scrap of energy in your body, every calorie you have ever eaten, traces back to sunlight, to the light of this one star falling on this one world and being caught by living things and passed along. We are, in the most literal sense, creatures of the sun, built and sustained by its warmth across billions of years. And now, for the first time, one of those creatures has reached back. The thing the sun made has flown into the thing that made it, and returned, and begun to understand it. There is something in that closing of the circle that feels older and larger than a science mission, something that touches on the oldest relationship there is, between a source of life and the life it gives rise to. We were born of the sun, and we went home to it, and we came back changed by the visit. And notice what kind of achievement this really was. It was not the work of a single brilliant mind, not one hero standing alone. It was the work of thousands of people across decades, engineers and scientists and technicians, most of whose names you will never know, each contributing a piece to a whole. None of them could have built alone. It was the work of a young man's stubborn idea in 1958, and the editor who chose to publish it, and the generations of researchers who carried the field forward, and the teams who designed the shield and plotted the Venus flybys and sat in that room through the silence. It was patience measured in decades, and cooperation measured in thousands, and a willingness to attempt something that had been called impossible, held steadily across a span of time longer than many of the people involved had been alive. That, as much as the spacecraft itself, is what touching the sun required. Not just cleverness, but continuity. Not just genius, but the long, shared, patient labour of many hands reaching together for the same impossible thing. For thousands of years we looked up at the sun and called it untouchable. And we were wrong about that too. We reached anyway. And what we found inside the fire is not only going to change how we understand the star, it may, in time, be part of what protects the fragile and luminous civilization we have spent so long building in that star's light. We touched the sun, and the sun, at last, is beginning to touch us back, not with a storm but with an answer.